Dear students, welcome to this lecture. So today I start with few properties of continuous function. So here is the theorem. So let f and g be two real valued functions such that f and g both are continuous at the point C. Okay, now then we prove that so first of all, f plus g, this is a new function, this is also continuous at C, and f minus g is also continuous at the point C. Okay, and we also prove that the product of the function fg, and it is defined by that pointwise multiplication, that is f of x into g of x, that is also continuous at the point C. And if f of c, say g of c, is not equal to 0, then we prove that we have already proved that then we have a interval containing c such that g of x is not equal to 0, right? We have proved that. Now here we prove that then the function f of g, f by g x, that is well defined, right? And which is defined by f of x by g of x. Now we prove that this function is also continuous at the point C. Okay, and we also prove that mod of f, this is also continuous at C, and we also prove that the function maximum of f of g and minimum of f of g both are continuous at the point C. So here is the proof of the property 1. So first of all, we have to choose one arbitrary sequence xn in the domain such that xn converts to C, right? Now let xn be an arbitrary sequence in the domain such that xn converges to C, right? Now it is given that f and g both are continuous at C. Now since f and g both are continuous at the point C, therefore f of xn and g of xn converts to f of c and g of c respectively, right? And now we can use the algebra of the sequence. Now that implies f of xn plus minus g of xn converges to f of c plus minus g of c, right? Now since my xn is an arbitrary sequence, so we can say that f plus minus g is continuous at C. Right? Now similarly we can prove the property too. So similar proof. Right? You can take an arbitrary sequence xn converts to C. Therefore f of xn and g on xn converts to f of c and g of c respectively. Therefore their product f of xn into g of xn converges to f of c into g of c, right? And similarly you can prove 3 as well. Now here we can write that since g of c is not equal to 0, so there exists a positive delta bigger than 0 such that g of x is not equal to 0 for all x belongs to that c minus delta comma c plus delta, right? So therefore f of x divided by g of x is well defined on the interval this c minus delta comma c plus delta, right? Now again you can choose one arbitrary sequence xn and we are done. Because let xn be an arbitrary sequence in the domain such that xn converges to c, right? Now since it is given that f and g both are continuous at c, therefore f of xn converges to f of c and g of xn converges to g of c, right? Now also it is given that gc is not equal to 0 and we prove that in that case g of x is not equal to 0 for all x belongs to that c minus delta comma c plus delta, right? Now since xn converts to c, therefore there exists n such that xn belongs to that set c minus delta comma c plus delta, right, for all n bigger equal to n. That's mean g of xn is not equal to 0 for all n bigger equal to n. Therefore f of xn and g of xn is well defined for all n bigger equal to n, right? Now therefore by the algebra of the sequence we can prove that f of xn divided g of xn is converges to f of c divided by g of c as n tending to infinity. Now since our sequence xn was arbitrary, so therefore f by g is continuous at c. The proof was simple, right? Now we can prove the fourth one, that is if f is continuous at c, then mod of f is also continuous at c, and this is also similar. Why? So let xn be an arbitrary sequence which converges to c. Therefore since f is continuous at c, so f of xn is converges to f of c. Now again by the algebra of the sequence we know that mod of f of xn converges to mod of f of c, right? So therefore mod of f is also continuous at c. Now by using this we can prove that maximum of f and g and also minimum of f and g are also continuous. Why? So note that maximum of f comma g, this is can be written as half into f plus g plus mod of f minus g, and also minimum of f comma g can be written as half into f plus g minus mod of f minus g. Right? Now we are done. Why? Because since f and g both are continuous at c, therefore f of f plus g is also continuous at c and f minus g is also continuous at c, right? Now since f minus g is continuous at c, therefore mod of f minus g is also continuous at c, right? Therefore their summation and their difference are also continuous at x equal to c. So we are done. Here is the complete proof as well. Now there is another interesting property of continuity is that composition of two continuous function is also continuous if the composition is defined. In other words, if f is continuous at C and G is continuous at the point f of C and say G composition f, which is defined by G of f of x, is defined, then the composition function f compose G, G compose f is also continuous at the point C. Okay, the proof is also simple. You can choose any arbitrary sequence xn which converts to C. Then f of xn converts to f of C and g of f of xn converts to g of f of C. Therefore, G compose f is also continuous at C. So the proof is very simple, right? Okay, so now these are all about the properties of continuous function. Now we shall discuss various types of discontinuity. So we can write types of discontinuity. Now first of all we have removable discontinuity. So let f, say d to r, be a function, right? And say a belongs to d. Now then we say f has removable discontinuity at the point A if limit x tending to a f of x exists but not equal to f of a. Okay, that's mean the limit of the function at x equal to a exists but the value is not equal to the value of the function at x equal to a. Okay, now sometimes if f is not defined at some point a but limit x tending to a f of a exists, then also we say that f has removable discontinuity at the point a. In the first case, if the limit of the function f at x equal to a exists but not equal to f of a, then we can redefine the function at x equal to a and we get a new function which is continuous at x equal to a, right? And in the second case, suppose f is not defined at all at x equal to a, but the limit at x equal to a f exists. Then we can define the function f at x equal to a as the limit of the function, right? And again we get a continuous function. Thus, if we have this kind of functions, then by defining or redefining, we get a continuous function, right? So for this reason, this kind of discontinuity is called removable discontinuity. Fine. Now we can see one example. Say f r to r defined by f of x equal to sin x by x when x not equal to 0 and equal to say 0 when x equal to 0. Right. Now here what is my limit? Limit extending to 0 f of x. Now we have proved that this limit is 1. This is 1, right? But this is not equal to f of 0, right? Now since the limit of this function exists but not equal to f of 0, see we can redefine a function, say gx equal to sin x by x if x not equal to 0 and equal to 1 if x equal to 0, right? Then that will be a continuous function. Now this is called removable discontinuity at x equal to 0. Fine. Now there is another discontinuity. This is called jump discontinuity. Jump discontinuity, or sometimes it is also called the discontinuity of first kind. Discontinuity of first kind. Okay. Now if so, let again f d to r be a function and say a belongs to d, right? Then we say f has jump discontinuity at the point A if the left hand limit and the right hand limit at A are not equal. That's mean if limit extending to A minus f of x and limit extending to a plus f of x, first of all both exist but not equal. Okay, for an example, so if we take f say r to r defined by f of x equal to say 1 when x less than equal to 0 equal to say 2 when x bigger than 0, right? Now here you can check that limit extending to 0 minus f of x equal to 1 and the limit extending to 0 plus f of x equal to 2, right? So the left hand limit and the right hand limit at x equal to 0 both exist but not equal. Therefore f has jump discontinuity at x equal to 0, or we can say just at 0. Fine. Now there is another type of discontinuity. This is called essential discontinuity, or the continuity of second kind. Sorry, discontinuity of second kind. Okay, so again, so let f be a function and a belongs to D, right? Now if the left hand limit of f this or the right hand limit of f at x equal to a does not exist or infinite, okay, then we say f has essential discontinuity at x equal to a, or at the point a. Okay. Now sometimes we separate the discontinuity when the limit is infinite. So there is another type of discontinuity. You can say that infinite discontinuity. This is actually a part of essential singularity. Okay. Now this says, so let f d to r be a function and a belongs to D, right? Then so if the left hand limit or the right hand limit of the function f at x equal to a is either plus infinity or minus infinity, that is just infinity, then we say f has infinite discontinuity at the point A. Okay, so we can see few examples. Now let f of x, so f r to r be a function such that f of x equal to 0 when x belongs to rational, equal to 1 if x belongs to irrational, say r minus q. Show that f has essential discontinuity at each point, at each point C belongs to R. In fact, you can verify that for, say, R belongs to rational or C belongs to irrational, that limit extending to R plus f of x, limit extending to R minus f of x, limit extending to C plus f of x, and limit extending to C minus f of x, all do not exist. You can easily check that. I can solve one part only. So now first of all, let R belongs to Q. Then we can check xn equal to, say, R plus 1 by n, and let yn equal to R plus, say, root 2 by n. Okay? Then xn is rational and yn is irrational. Now then, both are positive, right? Now xn converges to R and yn also converges to R, and also xn comma yn all are bigger than R, right? But f of xn, so what is my f of xn? Now f of xn is 0 for all n, and f of yn equal to 1 for all n. So that implies f of xn converges to 0 and f of yn converges to 1 for all n, right? So you can write as n tending to infinity, right? So thus limit extending to R plus f of x does not exist, right? Now similarly, if you choose xn equal to here R minus 1 by n and yn equal to R minus root 2 by n, then you can check that limit extending to R minus f of x also does not exist, right? Now what if you choose your C belongs to irrational number, right? Now in that case you can find one. So here I write for C, say this is my C0, C1, C2, C3, C4. This is the decimal representation, right? Then you can one consider xn equal to C plus 1 by n, and another one Rn equal to C0 dot C1, C2, Cn. Or more specifically, you can write plus minus whatever you have the sign of C. Okay? Consider another example for infinite discontinuity. So here is one example. Say if be a function from R to R such that f of x equal to 0 when x is less than equal to 1 and equal to, say, 1 by x minus 1 when x is strictly bigger than 1. Fine. Now check that here limit extending to 1 minus f of x, that is 0, and limit x tending to 1 plus f of x, that is infinite, right? So thus we say f has infinite discontinuity at 1. So here we can say that f also has essential discontinuity at 1 as well. Essential discontinuity at 1 as well. Fine. If f is a continuous function on a closed and bounded set or on a closed and bounded interval, then f has some beautiful properties. Now we shall study these properties. So here is the first result. Now this result says, so let f a to r be a continuous function and a is a closed and bounded interval. In fact, you can take any closed and bounded set. So we can write closed and bounded set, then f is bounded. So first of all, we recall the definition of a closed set. So a set is said to be closed if it contains all of its limit points, right? That's mean whenever you have a convergent sequence xn where xn belongs to the set A, and if xn converges to a point C, then the set A should contain the point C. Okay? Now this is the definition of a closed set, right? Now we recall the theorem, the famous theorem called Bolzano-Weierstrass theorem. For a sequence. Now this theorem says every bounded sequence in R has a convergent subsequence. Okay, so we have seen this theorem. Now by using this theorem we shall prove these properties of f. Okay, so here is the proof of the above theorem. That is, if f is a continuous function and the domain is a closed and bounded set, then the function f must be bounded. So if possible, let f be not bounded. So we first assume that, so if it is possible that f is not bounded, then what will happen? So then for each natural number n, right, we must have at least one point in A. We can write xn belongs to A such that mod of f of xn bigger than n, right? Since f is not bounded, that's mean whenever we choose a number, so the value of f, that is, there should be some point in A such that the value of f at that point must be bigger than that number, right? So here we write only that. So that's mean we get a sequence xn, we can write here, get a sequence xn in A such that mod of f of xn bigger than n. Now what can you say about the sequence xn? It can be convergent or it may not, right? But since A is a bounded interval, therefore the sequence should be bounded. So since A is bounded, right? So the sequence xn is a bounded sequence. Right? Now since the sequence xn is a bounded sequence, so by the above theorem, that is by the famous Bolzano-Weierstrass theorem, we get a convergent subsequence, right? Therefore by Bolzano-Weierstrass theorem, there exists a subsequence, say xrn of xn, such that xrn is a convergent subsequence, right? That's mean we can write xrn converges to C as n tending to infinity, right? Now we know that A is closed, right? Now since A is closed and xrn is a convergent sequence in A, right? Therefore, and we can write that xrn converges to C. Therefore, by the definition of the closeness, we can say that C belongs to A, right? That's mean we have a convergent sequence xrn such that xrn converges to C and C belongs to A. Now since C belongs to A and f is a continuous function on the set A, therefore f is continuous at the point C as well. Now since f is continuous at C because C belongs to A, right? Therefore, or you can say and xrn converges to C, therefore f of xrn should be converges to f of C by our definition of continuity, right? Now this implies mod of f of xrn converges to mod of f of C, right? And that mod of fc is a positive real number, right? But by our construction, what was my f of xrn? That f of xrn was strictly bigger than the number rn, right? And this is strictly bigger equal to n, right? Now this implies mod of f of xrn, that is diverges to infinity as n tending to infinity, right? Now this is a contradiction. So we assume that the function f is not bounded and we arrived at a contradiction, right? So therefore the function f must be bounded. F must be bounded. Now there is another beautiful properties of R when the domain is closed and bounded interval. So let f closed interval a b to R be a continuous function. Okay, now then this theorem says the supremum and infimum of the function f are achieved in the domain closed interval a b. Right? So this is the beautiful properties when the domain of the function is a closed and bounded interval. So here is the proof. So first of all, by the previous theorem, I can write by the previous theorem, we have f is bounded. What does it mean that f is bounded? That's mean the set f, that is the image of AB, right? The set is a bounded set in R, right? Now this is a bounded set in R, that means it has a lower bound and it has an upper bound. Therefore, by the completeness properties of R, we know that this set has a supremum and has a infimum. Now, by the completeness property of R, we have that set has a supremum and an infimum in R, right? Now let capital M equal to supremum of the set this, and which is same as supremum of the set f of x where x belongs to closed interval a b, and let small m equal to infimum of this set, that is the image of the interval a b, equal to infimum of this set, right? Now see, for each natural number n, if we take m minus 1 by n, then this is not an upper bound of the set f of ab, right? So that's mean for each n there exists an element, say xn, belongs to that set ab such that m minus 1 by n is strictly less than f of xn greater equal to m, right? Because since m is the supremum, therefore m minus 1 by n, this is a strictly less than m, right? So this is not an upper bound. Therefore we must have one value, say f of xn, which is lies between m minus 1 by n and m. Fine. Now this will imply xn is a bounded sequence in the closed interval AB such that f of xn converges to m, right? Since f of xn lies between m minus 1 by n and m. If n tending to infinity, so f of xn must converge to m, right? Now similarly, we can write that for each n natural number, there exists yn such that m less than equal to f of yn strictly less than m plus 1 by n, right? Because m plus 1 by n is not an lower bound, therefore there should be a number f of yn, right? That's mean yn is a bounded sequence in the closed and bounded interval AB such that f of yn converges to the number m as n tending to infinity, right? Okay. Now note that here we do not know our sequence xn and our sequence yn are convergent or not. But we can use the Bolzano-Weierstrass theorem and we get there exist convergent subsequences, say xrn and yrn of the sequence xn and yn such that xrn converges to say a number c and yrn converges to number d respectively, right? Now since that a less than equal to xrn less than equal to b and a less than equal to yrn less than equal to b, therefore we have a less than equal to the limit c less than equal to b and a less than equal to d less than equal to b, that is the limit c and d belongs to the closed interval a and b, right? Now since this limit that c and d belongs to the domain because of the closeness of the set of the domain, right? So we can use the definition of continuity. Now since f is continuous at c and d, right, and xrn converges to c and yrn converges to d, so we have f of xrn converges to f of c and f of yrn converges to f of d. Okay. On the other hand, note that f of xn converges to capital M and f of yn converges to small m, right? And xrn and yrn was the subsequences of fxn and yxn, right? So therefore f of xrn also converges to m being a subsequence of xn, and f of yrn also converges to m being a subsequence of f of yn, right? Now since the limit of a sequences are unique, therefore f of c equal to m and f of d equal to small m. So thus we are done. So this completes the proof. That's mean if we have a continuous function whose domain is a closed and bounded interval, then we can say that f is bounded and the supremum and infimum are achieved in the domain. Now what if we have the open interval domain? So if the domain of f is open interval, then we cannot say anything about the boundedness of a. For an example, so let f of x equal to 1 by x on the open interval 0, 1. Now then you can check that f is continuous on the open interval 0, 1, but f is not bounded. Right? Because if limit x tending to 0, that is x tending to 0 plus, then f of x tending to infinity, right? But if we choose my function f of x equal to say sine 1 by x, again on the open interval 0, 1, then you can see that f is continuous and as well as bounded. Then f is continuous and also bounded on the domain 0, 1. That's mean if the domain is an open set or open interval, then we cannot say anything about the boundedness of a. So f can be bounded or f cannot be. And if the domain is unbounded, then also we cannot say anything about the boundedness of f, right? For an example, if we take just the simple function fx equal to say x on R, then f is continuous but not bounded. Right? On the other hand, if we take fx equal to just a constant function on R, then f is continuous and bounded. Right? Therefore, the domain is a closed and bounded interval. This is very important. There is another interesting property of a continuous function if the domain is a closed and bounded interval. So I write the result. So let f be a continuous function from the closed interval ab to R. Right? Now if f of a into f of b that is less than 0, then there exists a point C belongs to open interval AB such that f of C equal to 0. Okay? Now the proof is also simple. So first of all, without loss of generality, we can assume that say f of a, this is strictly less than 0, and f of b, that is bigger than 0. The proof of the case when f of a is bigger than 0 and f of b is less than 0 is very similar to this proof. Okay, so first let's see the proof of this case, that is when f of a is less than 0 and f of b is bigger than 0. Now since f is continuous at a and f of a is less than 0, therefore we have already seen that there exists a positive, say delta 1, such that f of x is strictly less than 0 for all x belongs to the interval a comma a plus delta 1. Okay, and similarly, since f of b is bigger than 0 and f is continuous, therefore there exists positive say delta 2 such that f of x is bigger than 0 for all x belongs to that open b minus delta 2 and closed b. Okay, and this is subset of AB. Fine. Now consider the set S, which is all the elements from the closed interval AB such that f of x is strictly less than 0. Then you can easily check that the set a comma a plus delta 1, that is subset of S, and S intersection the interval b minus delta 2 and closed b, that is empty, right? Because all the elements in this set has f of x is bigger than 0 and the elements from S has f of x is less than 0, right? Therefore their intersection is empty. Now first of all, since S subset of AB, right, that's mean S is a bounded set, or you can say that F is bounded above. Right? And you can say that B, or that B minus delta is an upper bound. Or you can say B minus delta 2 is an upper bound for S. Now since S is a bounded set in R, therefore by the completeness property of R, S has a supremum. So let C equal to supremum of S. Fine. Now note that, so this is my A, this is my B, right? And this is my say A plus delta 1, say this is my B minus delta 2, right? Now S intersect with this set is empty, okay, and this is subset of S. That means C should be bigger than this and should be less than this, or less than equal to this, right? So here C belongs to closed interval A plus delta 1 comma A minus B minus delta 2. Okay, so that's mean if we take the set C minus delta 1 comma C plus delta 2, that is subset of AB. Fine. Okay. Now what we will do, we will take, so let xn equal to C plus 1 by n. Now since C is a supremum, now since C is the supremum of S, right, therefore that C plus 1 by n, that is xn, is not belongs to S for all n. Therefore f of xn is bigger than 0 if f of xn is well defined. So first of all, we have to show that when f of xn is well defined, that is when xn belongs to that set A comma B. Now note that here xn converges to C, right? Therefore there exists natural number n such that xn belongs to the set C minus delta 1 comma C plus delta 2, that is subset of AB for all n bigger equal to n, right? Now that imply f of xn is strictly bigger than 0 for all n bigger equal to n. Okay? Now note that the point C belongs to the closed interval AB, and it is given that f is continuous on the closed interval AB. Therefore, f is continuous at the point C. So, since f is continuous at the point C and xn converges to C, therefore we have f of xn converges to f of C, right? And also, since f of xn is bigger than 0 for all n bigger equal to n, therefore we have f of C, we cannot say strictly bigger than 0, but we can say it is bigger equal to 0. Fine, right. Now what we will do, since supremum of S that is equal to C, thus for each natural number n, if we take C minus 1 by n, so that will be not be a upper bound for S, right? So therefore there exists yn belongs to S such that C minus 1 by n less than yn less than equal to C. Okay? Now therefore yn converts to C as n tending to infinity, right? Now again, since f is continuous at C, so f of yn converges to f of C. Again note that since each of yn belongs to S, yn belongs to S for all n, right? Now therefore f of yn is strictly less than 0. It was the definition of S, right? We have chosen S in this way, right? This. So therefore, if we take the limit, so f of yn converts to f of C, therefore f of C is less than equal to 0. Now here we had f of C is bigger equal to 0, and here we get f of C is less than equal to 0. So thus by 1 and 2 we get f of C equal to 0. Now since C belongs to closed interval a plus delta 1 comma b minus delta 2, which is subset of open interval AB, so we are done. Okay, so this completes the proof. Okay, so I stop here today. See you in the next lecture with few more properties of continuous function.